So in section 6.4 we're going to learn something new called polar coordinates. Rectangular coordinates, which we're more familiar with, give us two numbers. So if we look at 5, 7, that tells us on a coordinate plane to go 5 to the right and go 7 up, and we might end up something like right there. Polar coordinates are just a little different. They still give us two numbers, but the numbers stand for something else. So let me erase this a second. And if we look at part A, number 1, our polar coordinate is 2 pi over 3. The first number tells us how far to go. The second number tells us in what direction. And I usually start with the second number. So pi over 3 is 60 degrees. That means we're going to go somewhere out in this direction here. And the direction we want to go, or the distance we want to go is 2. So our final point for number 1 would be right about here. This would be point P. It's in the direction of pi over 3 and a distance of 2. Number 2, point Q, a distance of -4, a direction of 3 pi over 4. Well, 3 pi over 4 is 45 degrees. Then we go 90. We want to go 135 degrees. That's going to be out in this direction. But when we see a distance of -4, that actually means go backwards. So a distance of -4 backwards from this direction, that means 1, 2, 3, 4. Point Q is going to be right about here. We think of going in a direction of 3 pi over 4, and we go backwards 4 spaces. And number 3, point R, go a distance of 3 in a direction of -45 degrees. -45 degrees, remember, goes out in this direction. A distance of 3 in that direction gets me right about there. This would be point R. So those are kind of the basics. What we now want to do is figure out how we move back and forth between rectangular system, which we're more used to, and the polar system. So I'm going to just draw a little picture, a little sketch. You might want to do this on the right side of the box that you see on your notes. Let's say this is a normal coordinate plane. We're just going to look at the first quadrant. If I were to put a point right about here, we'd say we're going to go a distance of x to the right and y up. So this distance here would be x, and this distance right there would be y. And if I'm going to think about that in terms of a polar point or polar equation, I would think of the distance to that point. We would call that r, and the direction that we go is theta. And all of a sudden we have a right triangle. And so the way that we convert between the two systems is to think of this right triangle. So the 4 rules that we see up here all come from this. If we were to take, just if we look at the first rule, for example, x equals r times cosine of theta, we can say that cosine of theta from this picture would be adjacent over hypotenuse, that is x over r. And if we were to rearrange this equation, multiply both sides by r, we would get this rule right there. Very similar what you do for the second rule. You would just start with sine of theta equals y over r and solve for y. I think that the third rule kind of makes sense. You see the Pythagorean theorem there, x squared plus y squared equals r squared. And then the fourth one, just take tangent of theta, it's going to be y over x. And that's how we can convert between the two systems. The first 2 rules get us from the polar system to the rectangular system, and the second 2 rules will help us get from rectangular to polar. We'll go through a few examples of those. First one, find the rectangular coordinate of the point that has a polar coordinate of 2, 7 pi over 6. First thing I would do is just get an idea of where this is going to be. 7 pi over 6 is just a little over half of a turn. 6 pi over 6 is a full turn. 7 pi over 6 is related to a 30-degree angle, so we're going to go out in this direction, a distance of 2. So maybe right about here would be the point that we're looking for. Just kind of keep that in mind as we actually make the changes here. So according to the rules that we have in that box, we know that x equals r times cosine of theta. So if we plug in our values, I would get 2 for r, and cosine of 7 pi over 6. 7 pi over 6, we already kind of know where that is based on the graph that we see here. It's going to be related to a 30-degree angle, and that x value there would be negative square root of 3 over 2. So really our x value is negative root 3, or that's about negative 1.73. Do the same thing for the y value. So we know y will equal r times sine of theta. So we plug in the values, it's going to be 2 times sine of 7 pi over 6. Sine of 7 pi over 6 is negative 1/2, and so we end up with a negative 1. So our answer for this, the rectangular coordinates, would be negative 1.73, comma, negative 1. And if we go back to our picture way up here, that does seem to match up with where the point is. It does look like we would end up going a little bit more to the left than we do going down, so that's a good thing. Example 2. Find the polar coordinate that has the rectangular coordinates of negative 1, comma 1. Again, I would come up with a picture. Negative 1, comma 1 is going to be somewhere up here. Keep that in mind as we now find the polar coordinates. So again, going back to the rules in our box, x squared plus y squared equals r squared. Plug in the values that I know. We have a negative 1 that we're going to square, and a positive 1 that we square. It's going to equal r squared. And so we would get that r squared equals 2, which means r must equal the square root of 2. Okay, that tells us the first part of a polar coordinate point. Second thing is to find the angle, and they tell us for that we look at tangent of theta. Tangent of theta would equal y over x. Our y value is negative 1. I'm sorry, that's a positive 1. Over an x value of negative 1. So really we want to know where tangent of theta equals negative 1. We could go ahead and use our calculator for this. We could go back to our unit circle and try to think about where that would be true. If we were to use our calculator, we would find out that theta equals negative 45 degrees. That's probably what I would start with, and realize that by doing this we're going to have to use inverse tangent. And inverse tangent only works for quadrants 1 and 4. So it's telling us that the angle should be kind of going out in that direction, which obviously doesn't make sense for our picture. We need to realize that our calculator is only giving us a partial answer. We need to add half a turn to this, add 180 degrees. So when I do that, I'm going to end up with it pointing in the direction that I actually want to go. Negative 45, in this case, plus 180 gets me 135 degrees. So my polar coordinates for this would be square root of 2, comma, 135 degrees. That is the answer that I'm looking for. Now, before we go on to our last example for this video, it's important to note that with rectangular points, there's only one way to get to a point. You can only go right or left so far, up or down so far. There's only one set of directions that I could give you to get you to that point. With polar points, polar systems, there's actually infinitely many ways to get to the point. So if I am trying to get to this point up here, this is not the only possible answer. And so the next section of notes kind of talks about that. I could keep adding 360 degrees to this value, and it's going to keep telling me to get to the correct value or the correct point. I could think of pointing in the opposite direction, actually using this value right here and going in a negative distance. So as we kind of wrap up the question here, it says find two more polar coordinates for this point that has the rectangular coordinates of -1, 1. And so if I already have the answer of square root of 235 degrees, I could simply keep adding 360 to this. So that gives me square root of 2, 495. I could take 360 degrees away. I could add another 360, add another 360. It's going to keep going on forever. Or I could think about going in a negative direction, but point the opposite direction. So I could have started out with that -45 degrees that I originally found in my graphing calculator. And then I could keep adding 360 to that, still going in a negative direction. So -45 plus 360 gets me 315. And again, I could keep doing that forever. So one important thing to note is that with polar coordinates, there are going to be infinitely many ways to get to the same point. That's true with rectangular systems. That's going to do it for this video. We'll talk about the back page in class.